So we were talking about the turning effect produced in this loop, and since only these two segments are involved, so we have to calculate the torque acting on this segment 1 and the torque acting on the segment 3. We must correct it as torque 3. So the basic formula is for the torque acting on any segment is what? It is R cross F. R is the moment arm and F is the force acting on that particular line segment. So here, what is R? The perpendicular distance between this segment and the axis of rotation. This is our R. This the length of this whole side is B. This whole side has a length equal to small b, and this is half of that b, so we will write R equal to B by 2. And what is the force acting on this line segment? It is F1, and it was calculated in the last part as IAB. The angle between R and F, this is R and this is F, this angle is 90 degree. So sine of 90, because this is cross product, so we will write it as R F1 sine of theta, and since theta is 90, so sine of 90 is 1. The angle between this R and F is this 90 degree, and sine of 90 is 1. So here you will write just 1, which will give you B by 2 into B by 2 is written for R, and IAB is written for F1. So the same will be the value of the torque acting on this side 3, because everything is the same. The moment arm has the same value, B by 2. The force acting F3 on this line segment has the same magnitude as F1, and that was given by IAB. The angle again is the same, that is between R and F. R is this one, R is this thing, that is the perpendicular distance between the axis of rotation and the point of application of force. The perpendicular distance between the axis of rotation and the point of application of force. This is our R, and this angle is 90 between R and F. So again, the torque acting on this segment will also be B by 2 into IAB. And what would be the total torque acting on this whole loop is the sum of tau 1 and tau 2. So what would we get? We would get tau equal to, if we put tau 1 and tau 3, both are having the values B by 2 IAB, so this will be 2 times B divided by 2 into I into small a into capital B. So this 2 will be cancelled with this 2, we will be left with BIA. Now if we write it as I into, if we write it as I into A into B into the capital B, the capital B. Now what is this product? This is the product of the length and breadth. The length and the breadth. Length is B and the breadth is A. So this product gives you the area of the loop, the area of this rectangular loop. So the torque can be written as I, the current carried by the loop, into the area A of the loop, into the magnetic field B in which this loop is placed. So this is a torque acting on this single loop. If we have a coil having n number of loops, then the total torque acting on that coil will be equal to n times I into A into B. This would be the value of the total torque acting on coil of n turns, each carrying a current I, having a cross-sectional area A, sorry, not cross-sectional, it is the area A of the loop of each turn of the coil. The area A of each turn of the coil. B is the magnetic field in which this coil is placed. So the total torque acting on such a coil will be equal to n times I into A into B. So let's just recall what we have studied. The forces on the sides 1 and 3 are F1 and F3, and they have the moment arms about the z-axis, and that moment arm is having the length b by 2. B by 2 sine of theta means, since we are writing torque as Rf into sine theta, so R sine theta into F, R B by 2 into sine theta, so that the total torque on the loop will be torque is equal to 2 times IAB into B by 2 sine of theta. This is a general case if R and F have any angle theta between them. Here they are perpendicular in this particular case, but maybe there is some other angle theta between R and F, so this is the generalized case. So this is IAB is the force, and this is the moment arm, and we have R into F sine of theta. 2 occurs for the two sides 1 and 2. This is the total torque, which is the sum of the torque acting on side 1 and side 2. So this is 2 times this value, and 2 goes with 2, so we are left with IAB sine of theta. This is for a single loop. This is the torque acting on a single loop. So for n number of turns, we will write the factor n over here, n IAB sine of theta. And for theta equal to 0, there will be no torque acting on the loop. Now what does theta equal to 0 means? Actually now here the theta is between this A and B, this pole A. Like this is, this product AB is the area of the loop, and here it is the vector area. So as you remember, the vector area has a direction which is perpendicular to the plane of the area. So if A and B are parallel, that is the normal to A and B are parallel, then theta is 0 and the torque will also be equal to 0. So the torque will act on the loop as long as this area is not aligned with B, or normal to the area is not aligned to B. So the action of the torque is to align A with B. In other words, to align the unit normal N to A with B. When these two come in alignment with each other, that is the unit normal N aligns up with the field, the torque stops acting because theta becomes 0, and there will be no torque acting on the loop which is aligned parallel or